Hello all. Let's start with microcontroller circuit design techniques. So as we have already seen lot of like different kind of videos that I have released, and many places I have told you guys like what are the different things that we should look into while designing microcontroller circuit designs. So here I will be taking up one of the microcontroller that has been released by Texas Instrument, which is MSPM0L series. And in this MSPM0L series, this is actually M0 plus Cortex, ARM Cortex, and we will be targeting our device as MSPM0L1105. Very low end device, a very low cost device, and very useful for a lot of applications that we will look into the session one by one. So why don't we just list out what are the things that we will be doing during this particular session. Alright. So what we'll do is we'll try to understand the device details and features and resources that is available for any microcontroller that you are going to work with. Okay, I have already given you a lot of information about how to select a microcontroller, or what are the things that you should take care of while finding a microcontroller for your particular application or design. Then we'll talk about what are the applications. Then we'll go ahead with design development resources, as I already mentioned you. We'll talk about what are the different devices, development resources, all those things. We will also see device comparison from this particular data set itself, so that we can find out our best suitable device that we need to find out. Okay, we will also look into functional block diagram, which is a great place to understand complete functionality in one page. Okay, so in a single page you will be able to find out all the features and functionalities and a basic connection diagram that will be required for your microcontrollers. Then we'll see a basic schematic of this particular microcontroller, which we will make it unable to work normally. Like everything is fine, we will make it unable to have it programmed or debugging very easily. Then we have lot of design and implementation that we have done for lot of application, like LED drivers with motion sensors and all those things. We have a BLDC motor driver for low power application. We have battery charger monitoring systems, like low end battery charger monitoring systems. All those things we have done using this particular devices. That's the main reason I have taken this particular microcontroller into picture. Okay, so one more reason for this particular microcontroller is very low cost and very easy to design. We have an ample amount of microcontrollers and we will talk about them as well, but we'll start with one of them first. Then we will also see from the design point of view, these are not needed, but however these are very essential topics that we need to take care of, like what is my bill of materials, what are the PCB design guidelines or layout guidelines that we need to take care of, and then we will see assembly of this particular board, and we will test this board in our lab. Okay, so this will be a complete package of making you to understand what is hardware engineering and what are the things you need to take care of while getting into the hardware designs. And then a very simple programming procedure I will be giving you, but I will not be giving a complete idea about programming, because I may not know much about it. However, a basic skills I will be able to give you an understanding, like what are the things you need to program so that you can bring up your board. Okay, so my basic idea or basic target of the board is this particular MSPM0L1105. This is one device. Another device will be MSPM0L1306. So Texas Instrument has released one design and development board also, that is called evaluation board, or you can consider as evaluation kit. So based on that, this microcontroller, which is applicable for all the series of MSPM0L microcontrollers. Okay, so let's start. As we see, we are going to target the part number MSPM0L1105. If you want to go ahead with the product link, you can go ahead with this and you will be able to see a complete idea of this particular microcontroller that is looking like. So I'm opening it for you. You can see we have MSPM0L1105 It is 32 megahertz microcontroller with Cortex M0 plus MCU with 32 kilobit of flash and 4 KB of SRAM and 12 bit ADC. Okay, and you can see all the parameters and packages, what are the different packages available, what is the features available. We'll see one by one each one of them, what is the description that is there. Okay. If you want to know ordering quantities and all, then you can order a particular part number. You will see this is less than $1. You can see that, like if you talk about this particular part number that I'll be giving you, like a 20 pin VSSOP package. So this is less than $1/2, which is around, like around less than 30 rupees cost will be there in Indian rupees for 1000 quantities. So you are going to select a microcontroller of less than 30 rupees for your all the applications that you are going to have. Good. So this is the series that is very useful for your small consumer application or battery powered systems or industrial applications, and we are going to have a complete design analysis of this particular series microcontrollers. So before moving into that, what we'll try to understand is we'll try to get some highlights or some of the things that Texas Instruments has given from their product site itself. So it is a new microcontroller from Texas Instrument and very low cost with high efficiency Cortex M0 plus MCU portfolio to achieve embedded system more affordable. That's the main point they have told. Now if you see, find the right processing integrated analog features for any general purpose design. We can also see reduced design time from months to just days. So just within 1 or 2 days you will be able to design this particular microcontroller circuit, and in next 2 days you can finish up your layout design, and in more 2 days you can finish up your assemblies, and this is how within 1 week or something you will be ready with your board design itself. Otherwise you can directly buy a development kit is available in a day, and you will be able to start in backend how to design your particular application, and in the meantime you can design your own schematic as well. Okay, so this is going to like making the future of embedded possible with a scalable processing portfolio as well. Why scalable processing is because we will be developing, let's say 20 pin device. So it has microcontroller available from, let's say 16 pin to around 64 pin device. So you will be able to scale the same microcontroller programs or everything in any of these pin numbers microcontroller. That's the understanding about a scalable processing portfolio. Okay, so why don't we go ahead and look into the product portfolio that is available with MSPM0 series. Okay, so in MSPM0 series we have a 0L series and 0Z series. Okay, so 0G series is bit higher. So you can see we have the color of little bit bluish color or greenish color. You can see it is of 32 megahertz, and this is 80 megahertz, and this is 80 megahertz plus CAN facility. So CAN facility, it can be utilized in your automotive applications as well. And you can see we have just 16 pin microcontroller with 16 kb, 32 kb, 64 kb. We have VSSOP 20 package, we have VSSOP 24 package, we have VSSOP 28 package. So like this you can go ahead and find out whichever device you want to have. Okay, so my preference is always go ahead with this one, which is MSPM0L1105. If you are not able to solve this, then you can go ahead with 1305 or 1306. That will be little bit higher flash, and this will be with lower flash. Okay, so this is the device that I have always taken for my designs, and this device. Okay, coming back to 0G0 series also, so we have very high end devices which is going to have MSPM0 357. Okay, 3507. So 3507 you can go ahead. So this is going to be in VQFN 48 package or LQFN 48 package or LQFN 64 package as well. So this is the highest end device that is available with MSPM0 series. Okay, now we are ready to get into the device features that we have there in our target model. So target device is MSPM0L110506, like that. Okay, So as you can see, we have core which is ARM32 bits Cortex M0 plus CPU, frequency up to 32 megahertz. We are also seeing the operating characteristic is from -40 degrees centigrade to 105 degrees centigrade, and it can go up to 125 degrees centigrade for extended version also, and let us say -40 degree to 85 degree for lower version. Okay, so there are like 2-3 voltage temperature ranges device that is available. We have the wide supply voltage range which is going to 1.62 volt to 3.6 volt, so it can be utilized in even your 1.8 volt application or 3.3 volt application. So generally I am concentrating on 3.3 volt application. Okay, coming back to memory, so we will be having up to 64 kb memory, but our device will be having 32 kb memory only. If you talk about analog peripherals, then we have one 12-bit ADC. So 12-bit ADC is there, and we have total 10 external channels. And if you talk about configurable internal ADC voltage reference, then it can have V reference as 1.4 volt or 2.5 volt. Okay, we have one general purpose amplifier as well, and we have integrated temperature sensors. You can monitor the temperature of the microcontroller that we are working on. If you see optimized low power mode, so in run mode it is consuming less than 100 microamperes. So you can see it is just less than 100 microamperes per megahertz it is working. So let us say if you are working with 4 megahertz capability or something like that, 4 megahertz frequency, then you will be consuming, let us say, 400 microampere of current. That's all. If you are working with 8 megahertz, then you will be like wasting, let's say, around 800 microampere, less than a milliamperes you can consider. Okay, in stop mode and standby mode, these are way like down the current consumption, so it can be easily utilized in your battery powered system where you need to have very low power consumption requirement. If you talk about digital peripherals, so it has 3 channel DMA controller, it has 4 16-bit general purpose timers. Okay, and each with 2 capture compare modes or all those things. We have 8 channel of PWM, so it can be very much utilized in your motor driver applications for low power motor driver application. It has watchdog timer as well. You can see it has 2 UART interface. One can support your LIN or IRDA and DALI, and other one will be a normal UART. We have one I2C also, like I2C interface as well, and we have SM bus, PM bus, and wake up from stop mode as well. It has one SPI which supports up to 16 megabits per second data rate. So this is how you are going to have your MCU cost less than 30 rupees or around 35 rupees, and you're going to spend, let us say, 40 rupees or maybe 60 rupees maximum with all the systems and all, every peripherals, programmer, connector, power supplies, all those things. You will be able to design your system less than 60 rupees with a microcontroller. Okay, let's move to the other parts. We have internal clock, so you don't need an external crystal oscillator for the clock frequency generation. So it has internal clock of 4 to 32 megahertz oscillators with ±1% of accuracy. It has low frequency oscillator as well, which is 32 kilohertz, which is used in your RTO application. Okay, RTC application, like real time clock application. If you talk about data integrity, we have a cyclic redundancy checker, that is CRC 16 or 32. We have flexible IO features which is having up to 28 GPIOs, but our device is actually 20 pin device, so it will be having around 18 GPIOs. Okay, so we'll talk about that as well. So as you can see, we have package option. Before that, as I told you, we have two 5 volt tolerant open drain pins, so it has a capability of taking 5 volt input, or it can give you 5 volt output levels as well, based on the open drain capabilities. The best thing is it can be developed, like circuit is developed using just 2 wire serial debug. Okay, so SWD programming, just you need 2 wires, and those 2 wires later can be utilized for your general application also, like general GPIOs as well. If you want to, make it, you can make them. We have package option from, let's say, 16 pins to up to 32 pins in this particular series. Our aim is to go ahead with VSSOP 20 package. Okay, and we are going to take 32 kilobit kilobytes of flash with 4 KB of RAM, and this is 64 KB is there, but 05 we are going to consider the device. Okay, as you can see, this is the demo board that is looking like, which is developed by Texas Instruments. They have released this particular board for our development purpose, and you can see very tiny microcontroller that is looking here, and it has integrated uh, debug capabilities, like debugger and everything is already there, so you don't have to buy any debugger separately, and the same debugger can be utilized for programming your external boards also. That's the beauty about all these kind of developments. Okay, so you don't need to buy a separate debugger or programmer for programming your external boards that you will be designing. You can utilize the same demo board to do that job. Let's get into the application that it can be utilized for, that I have been always talking about. So you can see we have ample list of applications where this particular microcontroller can be utilized. We can see we have battery charging and management, like you can have a lithium ion battery charger or nickel metal hydride battery charger, or fault indicators, or like a status indications. All those things you need a very low count pin, and you will be able to design those systems by this particular microcontroller, which is MSPM0L 1105, that is there with our target. So 20 pin VSSOP package. Okay. You can also utilize this particular microcontroller into power supplies and power delivery systems. We have personal electronics, okay, like home electronics and all. We have building securities and fire safeties, where you will be needing one small chip, and there you need not to go ahead with very high end microcontrollers. If you need to talk about, let us say, connected peripherals and printers, there you can utilize. We have grid infrastructures, we have smart metering, communication modules. Best thing is you can utilize this particular microcontrollers in your medical and healthcare applications also. Let us say you have temperature sensor device, temperature measurement device, or NIBP modules where you need very low count of pin numbers, or you may need to have SpO2 systems and all. So those things, handheld devices are there, like home healthcare applications. So this particular microcontroller will be very handy. You can utilize in your LED driver circuitry with motion sensors and all these things later on, like they need very low count pin microcontrollers. So for lighting application, LED drivers applications and all, you can utilize this particular microcontroller. So as we can see, we have ample amount of like application from this microcontrollers. So if you learn one of them, you will be able to extend your knowledge to any other microcontroller as well. At the same time, you are going to gain a knowledge of designing so many systems with only one microcontroller session. Let's say maybe 1 hour or 2 hour you will be spending time here, and you will be coming to know almost everything. Okay. So I have pasted the datasheet link that is there. So I will be giving you this datasheet link as well later on. Maybe if we upload this particular session in YouTube or somewhere, then we'll be providing this data sheet as well. Anyway, you can find out very easily. You can type it MSPM0L 1105, and you will get into the product link page of the microcontroller of the Texas Instrument that we just now showed you, right? So you can see this particular microcontroller page you will get, and you have the data sheet available here. You can directly click and get this particular data sheets. Okay, and we have user guide as well to go into very deeper. Let us get into device comparison. So as you can see, we have MSPM 0506. So 05 is actually 32 kilobytes of flash, and 06 is 64 kilobytes of flash. Okay, so 05 is 32 kilobytes, and 06 is 64 kilobytes. That's the only difference that is there. And for low pin count, we have little bit less number of ADC channels, and for higher pin counts we have like up to 10 ADC channels. As you can see, we have only one general purpose amplifiers, that is op amps is there. We have UART, I2C and SPI, almost all are having 2, 1, 1. We have timers, all of them are having 4. We have GPIOs, as you can see. For lower pin count you have 13, and for the pins which we are using is VSSOP package, this one, and that is having 17 GPIOs. Okay, and the highest pin count, which is up to 32 pin VQFN package, that is going to have 28 GPIOs. We have 5 volt tolerant IOs, which is each one of them are having 2 pins, so both of them, I mean both 2 pins can be utilized for 5 volt application, and the temperature range is -40°C to 105°C. Okay, good. So this is what we have with the device comparison. Moving onwards, we are going to talk into functional block diagram. As I already mentioned you, this particular block diagram is going to give you an indication of all the peripherals and all the features that is available inside the microcontroller that you will be getting. So as you can see, we have debug pin like SWCLK and SWDIO, that is clock pin and data input. Okay, so this is for programming purpose. We have UART, 2 UARTs are there, one is UART 0, one is UART 1, and it has all TX RX pin as well as clear to send and ready to send, all those things are there. Okay, we have I2C pins, I2C is there, so we have I2C pin which is SDA and SCL lines, that is your data line and clock line. We have timers, so as you can see, timer timer G0, G1, G2 and G4 is there. So G0, 1, 2 both are having 2 channels, so both can be utilized in their complementary functionality as well, so that they can drive 3-phase motors as well. Okay, and at the same time we have one more extra channel which is timer G4, which is of again 2 channels. So you can see total 8 PWMs you can generate with this tiny small microcontroller. Now if we talk about the oscillator functionalities, then you can see we have system oscillator inbuilt inside. You have the functionality of using external oscillator as well, so that you will be having your oscillator pins, but internal is more than enough for very small applications that we are looking into. We have LDOs for core supply voltage, so we have V core, so that you should not load to outer voltages, and we have VDD pin and VSS pin, which will be utilized for your power supply to the microcontroller. Okay, and we have one reset pin also, which is called as NRST pin. I forgot to tell you about this FCC in pin. So if you want, you can utilize, and let's say a bigger microcontroller is there in your system, or maybe FPGA or something which is generating clock signal. That clock signal you can utilize this particular ROSC pin to clock this particular microcontroller as well. Okay. Coming back to watchdog timer, we have general purpose amplifier which can be utilized for our amplification purpose. Let us say we need one single buffer. You don't have to add cost to the system, so you can utilize the inbuilt general purpose amplifier. And we have ADC reference. You can see V reference plus and V reference minus. If you want, you can use externally also. At the same time, internal V reference is there. We have up to 10 channels, analog ADC channels, so up to 10 ADC values you can monitor at the same time. And we have SPI signal. So SPI is actually here considered as not MOSI MISO. We have POKI and PICO. Okay, so peripheral output, client input. Peripheral output is basically the target devices, and client input is this, but I mean, peripheral is the host and C is the client. Okay, the target device. And we have SCK and CS, that is chip select pin. So POKI, PICO and SCK and CS pin. We have DMA control, we have CRC, which is going to have a little bit of protection techniques and all. And this is how we have only one port pins, which is PAX, which will go ahead with, let us say, PA0, PA1, PA2 and up to around 28 pins. So it will go ahead with up to PA28. So this is all about complete block diagram that is there with this particular microcontroller. So hope you have now very good idea about what is there inside this. So anybody have any questions regarding this? I hope I am very clear about all the parameters that I have been telling you right now. Let's proceed next. If we talk about recommended operating temperatures, okay, so you can see we have recommended operating temperature. Why don't we do one thing? we will do a quick look into the data sheets and tell you like what are the things that we need to take care of, and then we will move back to this particular place so that like we can go ahead with our uh, presentations. So let's open the data sheet. We have opened here the data sheet. Okay, so as you can see, very first page you will get features and like all those things that we already explained. We have ample amount of applications and all. If you click one of them, you may get a reference design as well directly. So that's the beauty of this particular application that is being given by Texas Instrument. They have come up into blue color these days with a link to the design as well, reference design as well. Okay, this is the description that is there. Coming back to this functional block diagram we already saw. Now this is the beauty of this particular data sheets. Like they have table of contents where you will be able to find out where is my pin diagram, where is my pin attributes, all those things you can always see directly by going there. Okay, so you can see what is the pin configuration and how, and what is the pin names and their functionalities for different pin numbers and everything. Okay, so this is what I wanted to tell you. From the table of contents, we have a specification if you want to know what is the absolute maximum rating, what is the recommended operating conditions. So these things we need to always take into account while reading the data sheets. Okay, coming back to the power supply sequence, you can see like what is the sequence of power supply. If there are 2-3 power supplies that is there, that you can always have a look into account. And we have other peripherals. You can see a lot of peripherals are there, like digital IOs, then analog muxes is there, ADC is there, temperature sensor is there, reference pin is there. We have GPM and general purpose amplifiers, I2C, SPI, UART, timers and debugger. So all these one by one you can go ahead and see if you want to get into very deeply each and every parameters. However, we will quickly design our own microcontroller circuit. Then if you talk about detailed description, so this is the one which you have to always go into power management units. Okay, so this power management unit will tell you what is the power supply scheme or something like that. Coming back to other places, like we have DMAs. Okay, so let me just make it little small. So we have DMA, we have event outputs and all, we have memories, flash memories, we have SRAMs, like what is the memories and all. We have GPIOs, we have IO multiplexer is nothing but one IO can have multiple functionalities. Let us say it can work as a timer, it can work as a PWM output, or it is working as ADC output, it is working as general purpose GPIOs, all those things into same one IOs. We have temperature sensor, we have general purpose amplifier, all these. See, right now it was all specification and same details are there in detailed manner. Okay, so you can have a very good design as well. The last one I'll just tell you is here a bootstrap loader and serial wire debugger. So there are two functionality of programming this particular microcontroller using bootstrap loader. Using one UART pin you will be able to program this particular microcontroller. That's the beauty. So you don't have to utilize your debug serial wire debug interface. And typical application layout is also there, like you can have a look into typical application where they will be connecting all the required connections which is necessary for this particular microcontroller. And this is the best thing that is there, like tools and supports and support resources and all those things. So these 2 points you will be able to give you an understanding like what are the resources that is available with TI and what are the tools and software that will be needing. So basically we utilize CC Studio, okay, CCS, Code Composer Studio. Good. So as you can see, revision history will be telling you this particular device is very new, as I already told you. So this has been released in 2023 and this is very new to go ahead with your designs. Okay, so this was all about this particular microcontroller that I wanted to tell you. Let's now get into our page. So as I was mentioning you, recommended operating conditions, so you can go ahead and give 3.3 volt. Okay, and then we have core voltage which is 1.35 volt, so this will be coming up 1.35 volt. Then we have a capacitor placed between VDD and VSS. Recommended value is 10 microfarad. If you want, you can increase it to 22 microfarad also, but that is not needed. 10 microfarad is more than enough. Okay. Capacitor placed between V core and VSS is 470 nanofarad. So these are things that is given here. Only two capacitors are given here. One more decoupling capacitor will be needed along with VDD pin, which will be 0.1 microfarad. That is not mentioned here. Okay. As I already mentioned you, like for T version it is 105 degree centigrade, and for S version it will can go ahead with 125 degree centigrade also. Okay, so you can, if you have a higher temperature rating requirement, you can go ahead with S version. We'll tell you how to find out that particular devices. And the clock frequency is, it can go up to 32 megahertz by 1 flash wait state, and 0 flash wait state it will be working with 24 megahertz. Let's get into the thermal power dissipation capabilities. Okay, so as you can see, we have been talking about VSSOP package. So this VSSOP package has the capability of junction to case. Okay, that is going to be 29 degree centigrade per watt. It means for 1 watt of power consumption, your temperature increment will be 29 degree centigrade. Coming back to coming back to this other temperature characteristics, like we have junction to ambient temperature resistance, which is going to be 91 degree centigrade per watt. Okay, so this is what we calculated for the power consumption and temperature increment. However, for VQFN package it has very good results. Okay, so in VQFN package you can see the thermal to junction to case thermal resistance is just 28 degree centigrade per watt, which is almost closer to 29. However, for ambient thermal resistance it is way down compared to this one. Okay, so that's the reason VQFN package has better thermal capabilities compared to VSSOP package. However, this is suggested because of very the pins will be outside, you will be able to manage it easily. Otherwise, VQFN package pins are inside the package. Okay, it means what, like for 1 watt of power consumption, there will be an increment of 28 degree centigrade in VQFN and 29 degree centigrade in VSSOP at the junction of the IC. Let's get into the pin diagrams that is there. So as you can see, you can go ahead and see one by one. Right now I will be concentrating on this is 32 pin package, we have 28 pin package, we have 24 pin package, and we have 20 pin package. So the best part of this particular pin diagramming is they have given the colors and their functionalities as well. So the red color is power pin. So as you can see, we have V core, which is power pin, and at the same time VDD and VSS are power pins. Okay, so this is the beauty of directly going into the power pin, and you can mark them. Understood? Coming back to, we have reset pin. So you can see one reset pin is there, and that pin can be used as IO pin also. So there are high speed IO pin, HSIO. So we have HSIO1 and HSIO2. So there are two high speed IO pins, which is PA1 and PA19. Okay, so that is nothing but the debug pin also. So that one is definitely it has to be a high speed. We have green color, which is 5 volt tolerant. So green color is 5 volt tolerant. This is half is given in this also. It means it has high speed IO as well as it is going to have 5 pin tolerant capability also, and at the same time it is NRST pin also. Okay, so this is how the pin mapping is there with this particular legends. Okay, color coding that is there. And just remember we will be giving this information again and again and again. So we have PA0 and PA1, two pins in this particular microcontroller, which is having 5 volt tolerant with open drain capabilities. Okay, so open drain, it means if you have to get high in any of the open drain pins, what you have to do is, to get high we have to, let us say, connect it to 5 volt with, let's say, 4.7 kilo ohm, and this is how you will be getting your output. Got it? Two more pins are there, which is WQFN 16 pin and SOT 16 pin. So SOT 16 pin are used for very low cost device where you need to have very low end design, so that doesn't matter. However, with one design we will be able to extend our same design capability with any other packages. That is not a worry. Let's get into the ordering information that we want to find out. So how to order this particular device, a particular part number, how do you want to design? Okay, So as you can see, we have processor family which is MSP. So you can write down, I'll just write one device name for you. So I'll write down MSP, that is first one. Then M0 is the platform, so you write down M0. Then you are going to write down product family which is L for like L is there and G is there. So basically we'll go ahead with L. Okay. Coming back to device subfamily which is 110. Okay, so 110, 130, 160, all those things are there, so we'll go ahead with 110. And then we have 6, that is flash memory, so 6 can take a 5, 6, all those things are there. So that was there in the table. So this is going to have 6, it means it will be having 64 kilobytes of memory. If you write down 5, then it will be having 32 kilobytes of memory. Okay, so let us write down 5 with 32 kilobytes of memory. Then if you talk about T, then it is having temperature range. So if you write down T, then it will be having -40 to 105. And if you see this table, you will be able to see what are the different temperature ranges. So you can go ahead with S also, which will be going up to 125 degrees centigrade. Okay. And RHB is the package type. So package type, as you can go ahead with this particular table 5.1. Just now I showed it to you. Let me just show it to you here. So this is the table where you have the package information like RHB, DGS28, RGE. Okay, so RGE is nothing but for VQFN, or RHB is for VQFN for different packages like 28 pin, 32 pin and 28 pin. So we are going to go ahead with VSSOP20. So that will be DGS20. Okay. Good. So we will be writing down DGS20, and then R for distribution format, like whether it is reels or tapes. So you can keep it like, if you want a small tapes, you can small reels, you can put T, and large reels you can put R. So large reels will be having lower cost compared to small reels. And if you have no marking, then it will be in tube format or tray format, which will be having a discrete format. Okay. So this is the complete part number that we are having into account for our design at a head. Okay. Good. So now we are ready to go ahead with the design and development. So as I already mentioned, you can go ahead and download this particular kit, which is called as LPMSPM0L1306. This is a launchpad development kit. Okay. So that is developed on MSPM0L1306 board. Okay, which is 32 pin VQFN package. As I already showed you the board diagram. So board image was there, right? So this one will be the development board directly to get started with your design. Coming back to the power supply schemes. Okay, so as you can see in the data sheet, you will be able to find out this particular basic application schematic, which will be showing you what are the different different capacitor that will be connected or that is needed. So before seeing this particular diagram, what we do is we have to always see only one page in the microcontroller, that is called as power supply schematic. Okay, so this is the schematic that you have to read it. So if this much if you are able to read, you are very good to go ahead with a complete depth design in your circuit. Okay, so what you can see is I have just marked in red colors, that is the one which you have to always look into account. So we have TI recommends connecting a combination of 10 microfarad and 0.1 microfarad capacitor between VDD and VSS. Okay, that is one thing. So 10 microfarad bulk capacitor can be ceramic capacitors with very low ESR values. Coming back to NRST pin, so it must be pulled up to VDD pin. Okay, whichever is VDD that you are supplying, let's say 3.3 volt, otherwise it will not switch on. Okay, so and whenever you have to reset, then you have to press the button so that it can get reset. So external 47 kilo ohm pull up resistor will be required with 10 nanofarad pull down capacitor for most application. So these are the two things you have to understand, like a reset pin. So we'll show you how to connect them. Coming back to the system oscillator frequency, so that utilizes external 100 kilo ohm with 0.1% tolerance resistor. So you can connect one 100 kilo ohm 0.1% tolerant resistor on this particular pin to enable the internal switching frequency, okay, or oscillator frequency. If this function is not utilized, then you can utilize this PA2 for your digital input output functionalities as well. Now one of the pin is there which is called V-core pin, that is in internal power supply pin, which is of 1.35 volt. So you have to connect one tank capacitor of 0.47 microfarad, which it will again be ceramic capacitor of 0.47 microfarad, and we do not connect any other circuits on this particular pin to drive anything. Okay, so that's the understanding. The two more pin which I was telling you is open drain IO pin, which is of 5 volt tolerant pin. So there will be a pull up resistor required on these pins for like high I2C and UART functionals, and open drain IOs only implement a low side NMOS drivers. So anyway, this is what I wanted to tell you, like two 5 volt tolerant pin is there. So now if we see in the basic circuit, you will see that VDD is having 10 microfarad plus 0.1 microfarad on the ground. Let us say 3.3 volt is the power supply that is connected here. Okay, so that is done. Coming back to the NRST pin, so NRST pin, as they mentioned, you connect one external 47 kilo ohm resistor to the power supply, and then pull down with 10 nanofarad of capacitor. It is not microfarad, it is 10 nanofarad. Okay, and then connect it to NRST. Let's say we have switch reset button, so reset button you can connect it. So let's say it get connected here, and whenever you press it, it will get resetted. So this is what the working is. You don't look into this particular circuit, that is for different purpose, but we'll tell you how. We just press it, it will get reset. Coming back to this V-core pin, so 0.47 microfarad capacitor is connected to the ground. As mentioned, we have oscillator pin which is using 100 kilo ohm resistor with 25 ppm and 0.1% tolerance. Coming back to open drain pins, open drain pin, as you can see, we have requirement of pull up resistor on the same voltage level you have to use. You don't use other voltage level, just put it 3.3 volt. 3.3 volt if you want to use, you can use, or otherwise 5 volt also you can use. Okay, so it is having high voltage tolerance, so you can utilize 5 volt or otherwise 3.3 volt also, but open drain pin you will be having higher current capability. That's the only advantage. We have a debugger pin which will be attaching SWDIO and SWCLK, which will be connecting on for the programming of microcontroller purpose. Okay, so now we are ready with all the equipments and all the design and details that were needed for the microcontroller design. So let's get into the basic design that we are going to have. So I have developed a design for you which is going to be in this form. We have this particular microcontroller that is generated in this form, and what I have done, only change is pin number 6 and pin number 5, 6 and 7 I have taken out, which is VDD pin and VSS pin. Okay, power supply pin and ground pin, and rest all I have kept in the same order, like 1 to 20, 1 to 10 and 11 to 20. Okay, now coming back to the supply voltage, so we have VDD pin which is going to supply this particular microcontroller, which is designed like 3.3 volt regulator is there for that purpose, with 10 microfarad capacitor and 0.1 microfarad capacitor, decoupling capacitor. Okay, and this VSS pin is grounded, which is my digital ground. Coming back to other part, which is having V-core pin. So V-core pin is having 0.47 microfarad capacitor. As you can see, we have 0.47 microfarad capacitor to the ground. One more requirement was we have ROSC pin, which we will be needing 100 kilohertz of 100 kilo ohm of resistor. So you can see ROSC pin which is having, like for internal oscillator functionality, we have connected 100 kilo ohm of resistor with 0.1% tolerance. Got it? Next is we have V reference pin. So if you want to use internal voltage reference, you can connect directly with a capacitor of 0.1 microfarad, and it will be utilized as internal voltage reference. If you want, you can connect external voltage reference pin also, let us say 3 volt or 2.5 volt or whatever voltage level you want it, but it should be less than VDD voltage range, that is around 3.3 volt. Rest other pins I have actually mentioned for, let's say, like we have user buttons. So I have used here two user buttons, PB0 and PB1. Then I have used two dip switches, which is dip switches 0 and dip switch 1. Then we two more are there, which is dip switch 2, dip switch 3. Okay, so 4 dip switches are there. We have PWM pins, which is PWM 3. Then we have ADC channels utilized for ADC 2A, ADC 3A. Okay, So like A2 and A3, that's the reason I have named it as 2A and 3A. It will be easy for me to understand for my circuitry purpose. Okay. So as you can see, ADC signal is coming from let's say outside target board or somewhere, or maybe other parts of the circuit section. With one filter I have used and send it to the ADC channel of ADC 3A. Similar to that, another ADC monitoring is being done at ADC 2A. And this PWM3 can be taken out for the PWM functionalities, and these all circuits I will tell you. There is a on off functionality I have kept, like from external board we have a particular like signal which is coming as on off signal. So if you want to switch it on, this particular like pin will be taking as input and telling you that the particular microcontroller has been switched on or switched off. Okay. There are other, like we can utilize some enable function, let us say enable, so you can send an enable signal also to switch on a board or something like that, but I have not named it right now. So get into the next phase. This is already, I just now I explained you very clearly. You can see now that all these things are already explained to you. If you can see, we have reset pin, this open drain pins. So in open drain pins PA1 was there, so PA1 you can go ahead and pull up with 47 kilo ohm resistor, that is just now I told you. And at the same time PA0 also can be pulled up, so PA0 is also pulled up with 10 kilo ohm resistor. Okay, so you want, you can have, this is NRST pin, that's the reason I have pulled it up with 47 kilo ohm. If you want, you can make it 47 kilo ohm also, that's not a problem. Okay, now let's get into the microcontroller peripherals design. Okay, so very first thing that we need is we need to have a power supply. Okay, so for power supply I have used very small regulator, which is TPS 7A2433. Okay, TPS 7A2433. Okay, so this is the regulator which is having a capability of giving you around 200 milliamperes of current. So this particular microcontroller doesn't require more than, let's say, 10 milliamperes of current for complete circuit functionalities. So this is more than enough. Okay, I have designed this particular LDO with 10 microfarad capacitor. You can give it at the input, and 1 microfarad also, and plus additionally you can keep at the output side 10 microfarad plus 2.2 microfarad. If you want, you can always keep 0.1 microfarad capacitor for smoothing purpose, or like a filter capacitor kind of thing. So this is the understanding that we should have. There are actually other functionalities also, that's the reason I have connected here resistors. If you want, we can directly take VDD from outside, like there was a possibility like VCC was coming, which is 3V3, so directly I will put one resistor and this will be acting as a VDD. So this particular regulator will be not be needed. That's the main idea I was using, a resistor in the output and inputs. Okay, so whenever this VCC is, let us say 3.3 volt, what I will do is I will connect this resistor 0 ohm and I will dismount this one, so this will get disconnected and VDD will be coming from this particular VCC itself. That's the main idea. Coming back to there are some places where you can see like ground symbol has been used, this one and this one. Okay, so what I have done is I have sorted them to 0 ohm resistor so that both the grounds are same, but recommendation is you use only one ground. This is a very small system, so you don't have to utilize separate grounding. Okay, but since I had I had taken this particular circuit from the very first revisions and all, that's the reason I have not changed them. Okay, but latest circuits are changed with proper like design and reviews. We have connected one external connector which of 6 pins. So 6 pin is having with like target board connected to this particular pins, and as you can see this particular board is being driven by VCC voltage, which is of 5 volt, and there inside there are 3.3 volt regulators, and there is a PWM signal that was needed to drive that particular board. There is on off signal that is coming from that board, and there were like 2 ADC channels that were actually coming from that board to be monitored. Okay, so you can have this as output signal, okay, not the input signal. Okay, so you have to have a like a option of how to understand whether it is input port or output port. So input port means my board, MCU board, is giving signal to this connector, and output port means this connector signal is coming out and going into my microcontroller IOs. Okay, so that's the input and output. Okay, so hope you are now clear. We have two push buttons and we have dip switches, so we'll explain you this in very detail, but my main aim is to give you an understanding how you can quickly design one very small linear regulator. And this is a fixed regulator, that's the reason this FB pin resistors are not used. Okay, I have just given a dummy values. You don't look into the values of 1k 1k, they will be designed if it is a in adjustable format. Okay, but since this one I have used 2433, so 33 is for 3.3 volt. Okay, the reason this particular this particular regulator I have used is because this has various voltage ranges that is available. Let's say you can act up to, let's say, 1.2 volt or 1.5 volt, up to go ahead with 5 volt region. Okay, okay, all right, so let's get into the LED connections. So how we can connect different kinds of LED to my microcontroller IOs. So what you can do is, one of the method to connect LEDs are this one, which I have already explained you. So let's make it very neat and clean first. Okay, all right, so we have 3v3 that is connected. What I have done is, one resistor I have connected with one LEDs, and this is going to user LED 0 pin, which is going to be my MCU IO pin. Okay, so this is how you can drive one LED. So whenever this microcontroller IO goes low, like from high to low, my LED will start glowing. That's the main point that you have to have the understanding. Okay, why low? Because it will get grounded. It means it will see a power supply coming through the LED and it will start glowing. Same will happen with LED user LED 1, which is of different color. So let's say if you want, you can put, let's say, this one green color, this one red color. If you want more LEDs, you can put with one resistor and one LEDs and connect it to some other IOs. Let's say user LED 2. Now this user LED 0, 1, 2, these all are my names, which is going to be the name of the IO pins of my microcontroller, and this will be working. Another way of another way of driving the LEDs are this method. So what will happen is, like, user LED 2 is connected to the microcontroller IOs and connect through a resistor to your LEDs, and this will get grounded. So whenever my microcontroller IO is going high, then only it will start glowing. Okay, and whenever it is low, whenever it will be low, it will not glow. That's the straightforward driving of an LEDs. Okay, so the thing is, the microcontroller has very limited current capability. Let us say 20 milliamperes, or let's say 10 milliamperes, very small capabilities. Okay, so in that case this may be a difficult situation. So what we can do, another way to drive these LEDs are, let's say we can have MCU signal connected here at this point. Okay, so whenever we make it high, what will happen? This particular uh, MOSFET will get switched on, and this will give a path for the LED to run. So this 5 volt is connected from the power supply range, and you can trigger your, or you can tweak your values or change your resistors values accordingly to have the brightness or dim of this particular LED that you are connecting. Okay, so this is another method to connect the LEDs. So these are the three methods that I told you: from the power supply directly to the MCU, from the MCU directly to the ground, and from the MCU user IOs through a MOSFET, and this is how it will be working. So there are a lot of things that is done. You can connect one buffers, so that will be like, let's say, open drain buffers, and you have like MCU signal this side, and this open drain buffer will be driving all the LEDs one by one. Okay, so let us say 7-8 LEDs if you want to have. Put one open drain buffers, maybe non-inverting buffers or inverting buffers, anything is fine. Accordingly the LEDs can glow, high or low. Alright, so let's get into the another one. We have already seen this particular user LEDs and all those things. This particular method, actually I didn't tell you other time. What happens is, this particular method is actually utilized when my voltage range is very low. So let me give you an example. Let us say we have 5 volt. Okay, so 5 volt, you can directly put one resistor and send it to the LED, and it will start glowing. Similar to that 12 volt or something, you can go ahead and design your resistor according to requirement of the LED current. Okay, but what if that, let's say 1.8 volt is their power supply, and you are trying to drive one LED. So it is very difficult, because 1.8 volt may not be sufficient for the forward voltage of this LED. Okay, so that may be wrong. Okay, the only thing is, what is changing is, based on the voltage labels, my resistor value is decreasing. Okay, so as we are decreasing the voltage labels, voltage supply, we are reducing the voltage, reducing the resistance, like series resistance, and that's how current capability is being maintained, right? But you have to make sure at the same time the voltage drop of this particular LED must be less than 1.8 volt, or less than 2.5 volt, or less than 3.3 volt. Okay, or less than 12 volt, or less than 5 volt. So general LEDs voltage drops are around 2 volt to 3.2 volt or something. Okay, so this LED will not even glow. Okay, so in that case you have to understand, if there is a special case where there are some LEDs which are designed for, let us say, 0.7 volt voltage drop or 1 volt voltage drop, that's the different case. Okay, but I'm just giving you an option. For 1.8 volt option, you have to definitely go ahead with this MOSFET kind of drive. So MOSFET can be easily driven by 1.8 volt signal, and at this time you will be able to drive this particular LED to see whether my 1.8 volt is available or not available. So this is basically called as power supply monitoring. So 1.8 volt, whenever it comes, this particular this particular MOSFET will be enabled, and this is how this LED will start glowing, and you will see 1.8 volt was available. Okay, good. So this is what we have, a complete circuit diagram with our what is that, LEDs. Then we have like all LEDs are connected now. So I have removed the user push buttons, like push buttons was connected, now I have connected to LEDs. So this is what, like, for teaching purpose, or for making you understand each and every parameters, what I have done is, I have keep changing all the IOs for connecting the different IOs, like sometimes push buttons, then sometimes LEDs, and then sometimes ADCs, or sometimes I2C or PWM lines, or all those things. So the same thing will continue as usual. Now let's get back into the next one. We will be talking about user push buttons and dip switches. Okay, so let's talk about user push button and dip switches. So I have connected push buttons. So these are the push button that is connected, and user push button 0 and user push button 1. So what is going to happen? This particular pin is connected to the microcontroller pin, like this particular line is connected to my microcontroller pin. So microcontroller pin is actually seeing high right now. So right now it is seeing high. And whenever user is pressing the push button on this particular switch, then this will get grounded, and this will make it low. So whenever there is a low coming to the microcontroller pin, we will see that push button has been pressed, and it will read the IO signal, and this is how it will act. So this is how it is working. So you can see user push button 0 will be receiving a low signal, and this is how it will act, and maybe it can switch on something. Let's say it can generate PWM signal. Whenever that button is pressed, you generate PWM signal, or you make some of the IOs high or low. So like that is the, it is acting as an interrupt kind of thing. Okay, coming back to same thing with other push button. Now let's get into the dip switches. So dip switches, what happens is, basically if you see, let me just get into this page. What is happening? My microcontroller pin is connected to user dip switches 0, 1, 2, 3, 4. Okay, and whenever my slide switch is this side, then this is open. Okay, so it means it is grounded. So whenever this side is like towards 1, it is, if it is there, then this is open. So my microcontroller will see that my dip switch is low, so it will be seeing a low. Now whenever you push it this side, what will happen? This will go to high. So this is how it is working. Okay, if you want, you can give a small amount of resistance as well. Let us say 10 ohm or something like that in each of the line. So you can keep that, or 100 ohm you can keep. So 100 ohm will not make a difference of this 10 kilo ohm, or if you want, you can increase these values to 100 kilo ohms. That is also possible. So our dip switches and push button is done. Let's take a break for 5 to 10 minutes, and then we will try to resume the session again with all other functionalities like UART, USB UART, or I2C, or SPI, or PWMs, ADCs. There are a lot of different functionalities that I have actually developed it based on this particular microcontroller, and we'll resume this session maybe after 5 to 10 minutes. So after freshen up, we will be able to see each and every functionalities that is there with this particular microcontroller, so that you can have a very good understanding about how to develop the complete circuitry. And in short, just wait 2 minutes. What I'll do is, as you can see, this is the complete microcontroller circuit that I have developed here, and you can see I have named it as port name itself, so that I don't have to keep changing for my LEDs or push buttons or all those things. We will be accordingly working on. So you can see we have I2C connection, I2C connection, we have like PWM connection, we have ADCs connections, and we have port pin connection which will be used for some other purposes. We have external connector here. Then we have I2C pull-up resistors, so you can see pull-up resistors are there. Then we have ADC filters, so ADC filters is there, like RC filter is connected. Before that we should like amplify the signal, or maybe have buffers before that, so that before sending to the ADC of the microcontroller, so those buffers actually make sure the ADC working fine. We have this particular regulator which is generating a voltage from 5 volt to 3.3 volt, which is used as VDD, so directly it is connected here. Okay, and same way we have used like buzzers, so which will be used for some alarm purpose. Okay, so if you want to see little bigger, we have buzzers. And as I told you, like for ADCs, you have directly a one like ADC3, you can directly connect it to the filter and then send it to your pin. And at the same time, I think the pin numberings are not same, so pin numberings we have to like change it. I'll give you the exact circuit that we have developed it for you, but this is all the circuits are developed, right? So you can see we have buffers that is used, and it will be sent to the particular port numbers. And then we have IR sensor pin, we have RTC application, we have EEPROM application, we have temperature sensor applications with digital sensors, and all those things are there. So this is like one of the best idea, or one of the method that you can develop this particular circuit very quickly. All right, let's take a break for 10 minutes, and then we will start the session again. Thank you so much.